Have you ever run into a project where you wish you had more GPIO pins on your ESP board? Today I'm going to show you a simple way to use something called a port expander to add up to 128 GPIO pins to your ESP board using just 2 wires. We'll take a look at the pinout and wiring connections. We'll do a simple breadboard example, and we'll take a look at the ESPHome code to make this easy to integrate into Home Assistant. And at the very end, I'll show you kind of an impractical, crazy example of how I created 75 input and output pins using just 2 pins on a simple ESP8266. So hang around. Hi, and welcome to Resin Chem Tech. Now, you may not have done a project yet where you've actually run out of pins on your ESP board. But if that ever does happen, today I'm going to show you an easy way to add additional inputs and outputs to your ESP8266 or your ESP32. Now, there are a lot of different chips and options and available ways to do this out there, but the one I'm going to look at today is the MCP23017 16-bit I/O expander. Now, as always, be sure to check the video description for additional information, including links to a written guide where I'll have parts list, wiring diagrams, code samples, and more. With that, let's get started. Let's take a look at a really simple example of where you might need something like an I/O port expander. Now, this is kind of a silly example, but it is based on a real project that one of my subscribers was working on. Let's say we've got 8 cabinets, and each of those cabinets has a wired magnetic reed switch attached to the door. Yes, I know you could use something like Zigbee switches that wouldn't require any wiring, but for the purpose of this, let's say we've got wired switches. When we open each one of those cabinets, we want to turn on the light in that cabinet, whether that be via a relay or some other output source. Well, just that alone is going to require 8 digital inputs for our switches and 8 digital outputs to control our light source. So how do you do something like that with a simple single ESP8266? An ESP8266 only has 17 GPIO pins, and only a maximum of 10 of those are available for digital input or output. So you might be thinking, well, let's just move up to an ESP32. An ESP32 does have 48 pins, but not all of those are exposed on every board. And a maximum of 26 are available for digital input and output, but 4 of those are input only. So only 22 that could be used for input or output. And if we have something like maybe 10 or 12 cabinets, we're going to quickly max out the ESP32, especially if we want to do things like attach some buttons or some additional sensors. So how do we get around this limitation? Well, we can use something called the I2C bus on our ESP board, and we can attach an MCP23017 port expander. But by using just 2 wires or 2 pins on our ESP board, I can add up to 16 digital I/O ports. That alone is enough to cover the initial example, with plenty of pins left over on our ESP board. But what happens again if you've got that 10 or 12? What if you need more than 16 digital ports? Well, since this is I2C, you can run multiple devices on the same 2 wires. So I can simply add another port expander as long as it has a different I2C address. And if that's not enough, well, because the MCP23017 has addressable pins, it can have up to 8 different I2C addresses. We can continue to add additional expanders all the way up to 8 for a total of 128 GPIO pins, again, only using 2 pins on our ESP board. Now, you might be asking, how does this work in something like ESPHome? We'll get to that in just a second. First, let's take a look at the pinout of the MCP23017. It's actually pretty easy to use. We connect our voltage and our ground to the VDD and VSS pins. Now, this will operate off of either 5 volts or 3.3 volts. Since I'm outputting 3.3 volts on the GPIO pins from my ESP controller, I'm just going to choose to operate everything at 3.3 volts. Next, we hook up our 2 wires from our ESP board. These are the only 2 pins we're going to need, and that is our I2C pins for data and clock. Over here are our 3 I2C address pins. This is what allows us to connect multiple devices to just those same 2 pins. By taking each one of these pins and either raising it up to the operating voltage, in my case 3.3 volts, or connecting it to ground, I can change the I2C address. By using the combination of these 3, that's what gives me up to 8 different I2C addresses, and why I can add 8 of these devices to those same 2 pins on my ESP controller. Next is a reset pin. You can pull that load to reset the port expander. Normally, you're going to connect that to your operating voltage, pull that high. If you wanted to, you could connect a button, or you could actually connect that to a different pin on your ESP board to actually be able to reset the port expander. Then you have the 16 digital input and output pins, arranged in two banks of A and B. Now, those are arranged in two banks of A and B because of these interrupts. Now, what the interrupts do, it allows you to detect a state change on any one of those pins in either bank A or bank B, or they can actually be ORed together. You might have a special use case for that. I'm not going to be using the interrupt pins in my examples. Now, there are some limitations with these port expanders that you need to be aware of, especially when it relates to current. The maximum current you can output on any single pin is 25 milliamps, and all of your output pins combined can't exceed 125 milliamps. Be aware of that. In my case, where I'm actually going to be using LEDs, I'm actually going to be using resistors to limit the current total output on any given port expander. If you exceed this current, odds are the chip is going to overheat and eventually fail. One other thing I should mention about this particular port expander, it is a digital I/O expander. That means your inputs and your outputs can only be binary, on, off, true, or false. It won't work for things like temperature sensors or things that use analog values. For that, you need to use something like a multiplexer or a different type of port expander. But this will work well for anything that has an on or off state. So how does this work in ESPHome? Well, ESPHome has native support for the MCP23017 port expander. As you can see here at the top, the GPIO pins in the datasheet, which are labeled GPA 0 to 7 and B 0 to 7, are mapped consecutively in this particular integration from 0 to 15. So we define our MCP23017, we tell it what I2C address we're using. This is what allows us to connect multiples, and I'll show an example of that in a minute. And then we just define a normal GPIO switch for our outputs or binary sensors for our inputs, just like we always do. The difference is underneath the pin, when we would normally indicate a particular pin on the ESP board, we tell it to use our MCP23017, and then we can use the pin numbers 0 to 15. Okay, enough with the theory. Let's actually throw something together on a breadboard, test this, and take a look at the real ESPHome code that makes it work. To power my test setup, I'm going to be using my benchtop power supply that I built out of an old PC power supply. And it's nice because I can have more than one output. So I'm outputting 5 volts to one bus and 3.3 volts out to another bus. I'll explain why I can't run 3.3 volts off of the D1 Mini here. Really has to do with drawing too much current. But just know that I've got 5 volts running to one bus and 3.3 volts running to another. Here's what I've created as a simple demo to show you how you can use the two pins to get multiple input-output pins using this port expander. Now, I'm just using a Wemos D1 Mini, an ESP8266, really just to show you this can work fine with an ESP8266. Of course, it will also work with the ESP32. You would just need to substitute your I2C pins on the ESP32. Quick little recap again of our pinout. Here I've got my 3.3 volts and ground coming into my port expander. I've got my clock and my data, which again is the only two pins I'll be using on the ESP8266. These 3 yellow wires are setting my I2C address for the chip. Right now I'm pulling all 3 of those to ground, which gives me the default hex address of 20. My reset pin, I'm pulling the high, and then I have 5 inputs and 5 outputs connected. All this is running ESPHome, and right now it's very simple. All I'm doing is toggling each corresponding LED with the push button. Again, you probably can't see the individual colors there because they're being washed out on the camera. But you can see that I now have 5 inputs and 5 outputs from just these 2 pins on the ESP8266. And I still have 6 inputs and outputs available here that I'm not yet using. Now, I did mention that I'm using a separate power supply for my 3.3 volts versus my 5 volts. You might be thinking, why can't I power the 3.3 volt bus right off of this D1 Mini? Well, for this simple example, you probably could because it's not going to pull that much current. But if you start using multiples of these chips, remember that each one of these could draw up to 125 milliamps if you max it out. And if you actually use all 8 of them, that would be a full 1 amp. And even in my case, I'm planning on using 5 of them, and that's going to be north of 600 milliamps, which is really too much current to pull through this 3.3 volt pin. So in my actual install, I will be feeding the system 5 volts, but I'm going to use this little step-down buck converter, and I can take my 5 volts and step that down to 3.3 volts for this bus. And this thing will handle up to 3 amps, so it would be fine even if I wanted to use 8 of these port expanders. But let's take a look at the simple ESPHome code and how I set up these 10 inputs and outputs off of these 2 pins. Now, the ESPHome code that I'm using is very similar to the example I showed before. I'm going to define my I2C bus and tell it what pins I'm using. Then I'm going to define my MCP23017. I'm going to give it an ID that I can use for my inputs and outputs, and then tell it which I2C hex address I'm using. Remember, I pulled all those pins to ground, so mine is using a hex address of 20. Now I just define my inputs and outputs. For my outputs, I define switches. Again, I give it a name. This is my red LED. I'm telling it which MCP board I'm using by that ID number, and then I tell it which of those pins, 0 to 15 or A0 to A7, B0 to B7, that I'm using. So I'm using pin B0 in this case, so that is pin number 8. I do that for all of my other LEDs, and then I come down here to my inputs, which are my push buttons, and I basically do the same thing, telling it which board I'm using or which port expander I'm using and which pin number on that port expander to use. In my case, I'm actually having an on-press automation that all I'm doing is toggling on or off the corresponding color LED. It's really that simple to add, again, up to 16 digital input or output pins off of just those 2 on the ESP board. Need more than the 16 ports? No problem. You can add a second 16-port expander connected to the same 2 data and clock pin wires from our ESP8266. Once again, powered by 3.3 volts. The only thing we do different here is on these address pins, I'm taking this first pin and I'm bringing it high to the 3.3 volts while the other 2 are still at ground. That gave this a hex address of 20. This now has a hex address of 21. But yet off the same 2 pins, I now have 32 digital input output pins available. And you can continue to add on to those as much as you need, all the way up to a total of 8 of these 16 port expanders. What does it look like in ESPHome when you have multiple port expanders? Well, it's very easy. We just add the additional port expanders underneath our MCP23017 integration. Each one will have a different ID, and you notice each one also has a different I2C address. Then in our outputs, we simply refer to which of those expander boards we're using, and as you can see here, I've got a switch for each of the 3 boards, 1, 2, and 3. They're all 3 using the same pin number, but they're referring to different port expanders. In the same way on my inputs or my binary sensors, I can use 3 different boards, all of them using the same pin number, but again, it's referring back to the different port expanders. And that way, you can continue to add GPIO pins or input-output ports to your ESP board. So now let's take the concept of using multiple port expanders to build that clock you saw at the beginning of this video. Now let me state this right up front, and before you jump down to the comments, this is not the best way to build a clock. There are many, many better ways to build a clock than what I'm doing here. For one, the final version here is pretty impractical. Why? Spoiler alert, this is what the final wiring looks like. Yeah, good luck hanging that on your wall. But my purpose here is again to show you how to use multiple port expanders. In my case, I'm going to be using 5 port expanders to create a total of 75 inputs and outputs, again, off of just 2 pins on an ESP8266. So while I will cover how I built this clock, it isn't really meant to be a step-by-step how-to for you to duplicate this project. The goal here is for you to understand how you can use these port expanders to add a lot of additional inputs and outputs for an ESP8266 or an ESP32 should you need that in one of your future projects. So this idea came about a couple of months ago when I was browsing the local hobby store and ran into these little wooden clock faces. They were about $2.50, so I picked one up with no real idea what I was going to do with it. But when I started looking at port expanders, I thought, it might be an opportunity to use this clock face to create a bunch of individual outputs for the minutes and the hours with no real idea of what I was getting myself into. So I'll quickly cover the build of the clock face here if you're interested. If not, feel free to use the timeline down below to skip ahead. But I started out by using a compass to create a circle for where all of my minute LEDs would be installed. I then used a digital angle finder to make a mark every 6 degrees, which would give me my 60 LEDs for the full 360-degree circle. I then drilled each of those holes out to accommodate 3mm LEDs, which is what I used for the minutes. I then went ahead and cut a hole for my ILI 9341, which is really not a part of this project, but since I can't ever seem to cut a nice square hole with a jigsaw, I simply 3D printed a trim piece that would help cover up those rough edges. I then went out and gave it a pretty crappy paint job. I didn't spend enough time sanding between coats to make this look really nice, but I was a little bit rushed. Once that was done and dried, I flipped it over and installed the 60 LEDs for the minute on the back side. I used bare copper to create a ground loop that all of the ground wires from the LEDs would be soldered to. That way I would only need one ground wire back to my controller. As you can see from here, I also installed the ILI 9341. It's just screwed to the back. Again, as you can see, this has its own controller if you're interested in that and how it works with ESPHome. I do have another video on that, but it's really not part of this project. For the hour LEDs, I 3D printed these little enclosures that would help stop the light from bleeding over from one number to the next. I simply glued those into place and also attached those ground wires to my ground loop. And that pretty much completes the build of the clock face itself. So now I'm ready to move on to talk about the clock controller. These are all the power connections for the 5 port expanders and my Wemos D1 Mini. Now all these 3 power rails are all 3.3 volts. This is 5 volt, but it's only going to power this. For each port expander, just like I showed in the wiring diagram, we've got 3.3 volts and ground powering it. Then over here, the reset pin is pulled higher to 3.3 on all of the chips, and then we vary the ground versus the 3.3 connections on these first 3 pins for the address. So just in order, the hex address for each of these are going to be 20, 21, 22, 23, and 24. Those are all of the 3.3, 5 volt, and ground connections. Here's the board with all the I2C wiring completed. Once again, we're just using 2 pins off of our ESP board, a data and a clock signal. The blue wire is the data signal, and the yellow wire is the clock signal, running to each of the 5 port expanders. So with this wiring right here, I now have 80 digital inputs or outputs across these 5 port expanders. And the only thing really left to do is to wire in whatever inputs or outputs that I want. In my case, having 80, that's enough for my 72 LEDs for the clock face, plus maybe 3 or 4 push buttons to add some optional controls. And here's what's quickly becoming a Franken clock, but this is all the wiring for all of the outputs that will go to the actual clock itself. Again, 72 LED controls, 60 for minutes and 12 for hours will be controlled by these 5 chips with 3 input buttons as well. So now the remaining part is to actually make the connections for the outputs to the clock itself. Again, there are much better ways to build a clock, but all I'm really doing here is exploring the use of these MCP23017 16-bit port expanders, and this just seems like a good way to do it. Now my goal is to eventually move all of this to a PCB. It's one of the things I've wanted to learn, one of the things I've not done before, but I do plan on trying to move all of this and designing my first PCB and shrinking this down small enough that I can put it on the back of the clock. And you saw this picture before, my spoiler alert. It was quite a challenge getting all of those wires connected and into the right spots on the breadboard. And again, my hope is to eventually create a custom PCB and eliminate a lot of these wires. But for a breadboard bench test, it actually works. Let's take a look at the final build now that I have all of the LEDs wired and I have 72 outputs and 3 inputs. So go ahead and kick this off. First thing it's going to do is it's going to run a little system boot check just to check all of the LEDs, so the minutes and then the hours, and then what it's going to do is it's going to display the current time. Now the hours are a little bit brighter when you look at it straight on, but these LEDs are so bright it just overwhelms the camera, so I'm shooting at an angle. And of course the ILI 9341 display here in the center will eventually display the current day of the week and the date, but that has its own controller and is really separate. So it's not really practical, but it is a good example of using these port expanders, and I am running 75 inputs and outputs off of just 2 pins on my Wemos D1 Mini ESP8266. So that's my LED clock. As I told one of my subscribers on Discord, this would be what Rube Goldberg would create if he were to create a clock. But again, the idea here was to show you the potential uses of port expanders. Just some ideas that popped to mind would be something like maybe a model railroad situation where you had a bunch of individual LEDs that you wanted to be able to turn off or on in a situation where something like an addressable LED strip just probably wouldn't work very well. Or someplace where maybe you have a whole panel of input push buttons that you need to use. So let me know down in the comments if you've used these port expanders in your own projects or if you have ideas of where they might be useful. And if you've seen anything in this video that you like, do me a favor and hit that thumbs up button, click the subscribe button if you want to see more of my videos, and ding the little bell icon if you want to be notified when I release new content. As always, I'd like to say thank you for watching, and I hope to see you soon.